Multivariable Calculus 13.3, day 1, and we're picking back up from our part 1 video. Here's our part 2. We are really just finishing this up very fast. We are finding what the derivative of our unit tangent vector with respect to arc length is. And you can see it's going to be this right here. Now, of course, curvature, kappa, the Greek letter kappa, is going to be the length of that vector. Well, we already know that down below, r prime of t, that length, it's a constant. And we can actually slide that constant out. It's just like sliding a constant out of a vector. And so what you're going to see then is this. If we just found the length of our numerator, that would suffice. So very, very, very importantly, kappa is going to be the length of what we have for t prime of t. That's really what we have up here. If you think about it. So we've got our length of t prime all over that length of r prime of t. So this was the proof of the curvature formula. And, it's right here. Just need to put a vector arrow above in that numerator. So once you have that, then you can go ahead and quickly find what curvature actually is. So let's do that right now. Let's just say that we have a vector function, and they even tell you it's a circle of radius a. So tell you what, I'm going to very quickly find the derivative here, and I'm going to go into component form. Derivative of cosine is negative sine, so this hopefully will speed up the process a little bit. Likewise, the derivative of sine is cosine. And at this point, I'd like to find the length of this. You can see from our kappa formula that we just wrote, that's going to be something that we're going to need to do. Might as well do it right now. And as we're looking at this, I hope you can see very clearly that this is a squared sine squared plus a squared cosine squared. The negatives are going to go away. A squared, if we were to factor that out, you'd know sine squared plus cosine squared is 1. And the square root of a squared, because a radius is non-negative, we can say the square root of a squared is just an a. So let's take a look at our tangent vector then, our unit tangent vector. It's going to be r prime divided by the length of r prime. So in components, it's negative a sine of t, a cosine of t. But down here, we just found this to be an a. So we're saying more or less divide both components by the constant a. And we're going to be left with negative sine of t, cosine of t. Now we can go ahead and take our derivative. And as we have t prime here, in components, you can see we're going to have negative cosine of t and negative sine of t. And if we wanted to find the length, well, it would only take you a moment. It's negative cosine of t squared plus negative sine of t squared. Well, I think we can quickly see it's really cosine squared plus sine squared, which is 1. The square root of 1 is just a 1 itself. So what are we getting into here? Well, kappa, when they're saying find the curvature, you might remember from the formula that we had up above, we said, well, it's the length of t prime divided by the length of r prime of t. We just saw that this numerator is a 1. It's right up here. R prime of t, well, that was an a. So kappa is 1 over a. What you're going to notice is that for a circle, the radius is always going to be 1 over kappa, or you could say kappa is 1 over the radius. Okay, a couple of other quick formulas that we're going to work with. We don't have time to prove them. However, it's very, very helpful to not have to go through all the work of finding the unit tangent vector and then the derivative of it and so forth. So let's just say we have a vector function r. Kappa, the curvature, is the length of r prime of t cross-producted with r double prime of t divided by r prime of t's magnitude or length to the third. As some kids have said over the years, it's almost like they remember it's like a 1, 2, 3 kind of a formula. Those numbers show up in that regard. But once again, you can see, well, we're at a t. Well, here is our t, and our t is 0. So we want to find kappa at t equals 0. So that's been pretty prevalent, seeing that come about. So r prime, if we were to take a derivative real quickly, I think you could see things are going to work out nice and quickly. You can see we'd get a 1, a 2t, and a 3t squared. If I wanted to find a second derivative, well, that's really not so bad either. We can say that 0, the derivative of 2t is a 2, the derivative of 3t squared, that's a 6. And then I'm not going to take the time to go ahead and type this into the calculator for the sake of having a video here, but it's the cross product tool, and I trust that you guys can all do that. Forgive me, my last derivative, actually, I just noticed, would be a 6t, not a 6 for r double prime. In my haste here, I just wrote a 6, so please fix that. But as we go ahead and we do our cross product, I did that off to the side here. Actually, I worked it out by hand. But you can do that on your TI-89, and you can do that very, very quickly. Just use the cross product menu in the catalog. Then you can even find the norm. You can find the norm of that answer. The norm is the magnitude of whatever you had just found. It's the length of that vector. And certainly you can just do the Pythagorean theorem, like square root of all these terms squared. But it does not take you too long to get this confirmation either. This reduces it quickly for you too, so you could get the length of r prime crossed with r double prime. While you're at it, then you can also, by hand or with the norm tool, find the length of r prime. You can see if we square those, we get 1 plus 4t squared plus 9t to the 4th, and we'd have the square root of all of that. I'm going to write that in descending order, and you have this. So, what you more or less have then is following this formula, kappa, and I'm just going to write this down right here. It's the length of that cross product. That's going to be 2 radical 9 t to the fourth plus 9 t squared plus 1 divided by the length of r prime. But remember, we're going to have that whole length raised to the third power. And we want this. This would find you the curvature anywhere, but we're going to plug in a t equals 0. And you can quickly see that your numerator is going to be a 2. When you do that, your denominator, let's just check that through, you can see is going to be a 1. So your curvature is just going to be a 2. One final curvature formula is very helpful because this one is going back to function mode, and in function notation, it's the two-dimensional plane curves that we know so well. So, this is our f right here. You can see I don't have time to prove this one either, but it's the absolute value of the second derivative all over 1 plus f prime of x squared, but take that quantity and raise it to the 3/2. So real quickly, we're going to be doing this at the point 1, 1. That's x equals 1. So f prime is going to be 3x squared, if we've got y equals x cubed. F double prime is going to be 6x. So kappa, following this formula right up here, is going to be the absolute value of 6x. Down below we'll have 1 plus, well, that'll be 3x squared, that's f prime of x, but we'll have to square that and then raise it to the 3/2 power. But of course we're going to be plugging in a 1, 1. So what's our numerator? Well, it's going to be the absolute value of 6, which is just a 6. Plug in a 1 right here. 3 times 1 is 3. Square it, you get a 9. 9 plus 1 is 10. It's okay for kappa to be an ugly non-integer number. And that's your curvature, 6 all over 10 to the 3/2.